If you've happened to take a geometry class before, you may be familiar with the terms parallel and perpendicular. And in that setting, you may have defined parallel as two lines that extend off forever but never intersect, but never meet. And those might look something like this, right? Defined by no intersection. And perpendicular lines, they do meet, but they're defined by meeting in a particular way. That is, they will meet and intersect at a right angle. And so that might look something like this, right? Where their intersection is a right angle or a 90-degree angle. And so these are defined by intersecting at a 90-degree angle. And these are fantastic definitions for their purpose and really useful, particularly when thinking intuitively about these two concepts. For our purposes though, in terms of linear functions and equations, defining these a little different is actually going to be more useful. In particular, we'll define them in terms of slope, and then use that definition to be able to solve some more problems related to linear functions. So how do these two concepts of parallel and perpendicular relate to slope? Well, let's start with parallel. And if we imagine that we were to draw two parallel lines, what we would notice here, number one, of course, is that they don't intersect. But number two, these lines have that same degree of slant, right? They're both increasing and both increasing by the same rate. They're both just as steep. In other words, as we now know, they're both going to have the same slope. And so this gives us a new context, a new frame at which to look at the concept of parallel lines. We can say that two lines are parallel when they have the same slope. And so if this is y1 equal to mx plus b, just calling it y1 to label it as 1 compared to this other line here, which we'll call y2 equal to m2x plus b. The slope m1 of our first line has to equal the slope m2 of our second line when they're parallel. Now we should note here there is a little bit of a nuance to pay attention to when it comes to vertical lines, right? So if we note vertical lines have an undefined slope, but any two distinct vertical lines will also be parallel with each other. But any distinct vertical lines will also be parallel. Now perpendicular lines, on the other hand, they work a little bit different. As we can still see here, we can still think of these as two lines that intersect at a 90-degree angle, but we also want to frame this again in terms of slope too. Now, maybe unlike parallel, where we had the clear visual of those same slopes, the same degree of steepness, the relationship between two perpendicular lines and how that relates to slope is definitely not as immediately clear just from the visual. But what we can say is that two lines are perpendicular when the product of their slopes is equal to -1. In other words, if we call this line y1 equal to m1x plus b, and this line y2 equal to m2x plus b, then if these lines are perpendicular, what we'll have is m1 times m2 equal to -1. Now this might seem unusual at first, but another way to think about this, rather than just saying the products have to equal -1, would be to say that their slopes have to be opposite reciprocals. For example, if one had the slope of 4, the other would have to have the slope of -1/4, right? Because 4 times -1/4, that opposite reciprocal, you multiply by -1 and flip the fraction, the product of those two equals -1. And while it's tough to get a feel for why this might be the case, we can at least try to observe it. And so if we pull up Desmos and we graph y is equal to 4x, and y is equal to -1/4 x, we can see that these do really meet at a 90-degree angle. These are in fact two perpendicular lines. And again, where the slopes of each are opposite reciprocals, where here we have 4, here we have to have -1/4. Similarly, if here we had 3/2, here we would have to have -2/3, and those would be perpendicular as well. Then lastly, similar to parallel lines, we want to make a note here about vertical lines in particular, since those have an undefined slope. And we'll note that, as you might expect, vertical lines are perpendicular to horizontal lines. Vertical lines are perpendicular to horizontal lines. Now, with this new understanding of perpendicular and parallel through the framing and perspective of slope, we're going to be able to solve a bunch of new problems featuring linear functions and using the concepts of parallel and perpendicular. So for example, we might want to find the equation of a line perpendicular to y is equal to -2/3 x plus 3 that also passes through the point 1, 1. And so to give us a sense of what we're looking for ahead of time and how we can kind of picture this in our minds, we can pull up a graph here. If we come back to Desmos, we can see we've got our line in purple here, our -2/3 x plus 3, and then our point in blue, 1, 1. And so what our goal is going to be is to find the line that is perpendicular to that purple line, but also runs through the blue point 1, 1. And so how might we do that? If we recall from our previous video on point slope form, we know that all we need to write the equation of a line is a point and the slope. And so we need slope m and a point x1, y1. And that's going to allow us to utilize the point slope form of y minus y1 equal to m times x minus x1. Now we already do have a point, right? We have this point 1, 1 that we know our line is passing through. And so we're already halfway there. The only trick now is to see if we can figure out what the slope has to be. And this is where our new knowledge of perpendicular and parallel lines comes into play. And so we can use that to our advantage to find our new slope. Specifically knowing that m1 times m2 has to equal -1. In other words, we need the opposite reciprocal. And so if we call our original line here, y is equal to m1 times x plus 3, and m1 is equal to -2/3, that's going to mean that m2, the slope of the line we're looking for, is the opposite reciprocal of that. So it's negative, the opposite of that must be positive, and so we'll need a positive. It's 2/3, and so the reciprocal of that will flip that around, flip that over, giving us positive 3/2. And again, this being the opposite reciprocal. And to check ourselves here, we can confirm that their product is equal to -1. If we multiply -2/3 times 3/2, then we cancel out the 2's and are left with -1. We cancel out the 3's and are left with +1, giving us -1 times 1, or simply -1, as we'd expect. Now with that new slope and with the point we were given, 1, 1, we can use both of those along with the point slope form to write an equation for the line we're looking for. And so we'll use the point slope form, and I'll just abbreviate that P-S. So point slope is y minus y1 equal to m times x minus x1. We know that our point is passing through 1, 1, and so that's going to give us y minus 1 equal to m times x minus 1. And we know that our slope, as we just found, is going to have to be 3/2. So we can go ahead and plug that in here and have y minus 1 equal to 3/2 x minus 1. Simplifying this from here, y minus 1 is going to equal 3/2 x minus 3/2 as we distribute that 3x to both terms. And then solving for y to get this as an explicit formula, we will add 1 to both sides, giving us y is equal to 3/2 x minus 3/2 plus 1. We can also think of 1 as 2/2. And so if we are subtracting 3/2 and adding 2/2, that's going to be a total of minus 1/2. And so that gives us our equation. Y is equal to 3/2 x minus 1/2. We can take that now, come back to our graph, and plug in y is equal to 3/2 x minus 1/2. And we can see here that this is indeed perpendicular. We can see the right angle at the intersection and does in fact pass through the point 1, 1. And so we can graph this and confirm that it is indeed correct. Now it's worth noting here too that we could solve exactly the same problem but find a line that is parallel and runs through a given point, just utilizing the fact that these would have to have the same slopes. So rather than finding the opposite reciprocal and plugging into the point slope form, we would just take the same slope as the line we were given and utilize that with the point slope form. The rest would follow in exactly the same manner. And so I would encourage you to give this same problem a try, but trying to find a line that runs through the point 1, 1 and is parallel to the line that we were given, the negative 2/3 x plus 3. And so hopefully you found this video helpful. Hopefully it was a worthwhile exercise in recontextualizing some information you may have learned in geometry and pairing that with some new stuff we've learned in the past couple videos to apply both in a new way to solve new types of problems. As always, if you do have any questions, please let me know. I'm happy to help, and otherwise have a great rest of your day.